Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, presenting a topic, bipolar junction transistor. We had already started this bipolar junction transistor in the last lecture, and we are just continuing the bipolar junction transistor. I'll show the slides where we had completed and from where we are going to start. Okay, just wait a minute. Bipolar junction transistor, this is the basic definition we had covered. The symbolic representation of transistors, NPN and PNP. Brief history about the transistors. What do you mean by the transistors? What are the disadvantages of vacuum tubes? Earlier to the transistors, there are vacuum tubes were be used as an electronics device for a specific purpose. But after the invention of transistor, vacuum tubes are replaced, and these are some disadvantages of the vacuum tubes. Advantages of the transistors, and there are having some disadvantages of the transistor also, which we had discussed. This is the basic classification of transistor. The transistor is basically classified into two types of transistor, BJT and FET, bipolar junction transistor and field effect transistor. And further, field effect transistor is further categorized into two categories. One is JFET, junction field effect transistor, and MOSFET, metal oxide semiconductor field effect transistor. And further, they are more classified under the subcategories of the depletion and enhancement type mode. And further, they are just again classified in N channel or P channel type MOSFET or JFET. So this is all we had covered. Now, if we are talking about the nomenclature of the terminals of the BJT, emitter base collector, so we know about the emitter, base, and collector because the transistor is made up of three semiconductors, NPN or PNP type semiconductors are there. The various applications and the BJT operation modes, there are four modes of operation of the BJT, that is active mode, cutoff mode, and saturation mode, and inverted mode. So basically, active mode is used for the amplification of the signal, whereas rest of the are for the switching purposes. The saturation mode, NPN transistor, working of NPN transistor, we had seen this, we had completed this. Now, biased NPN transistor for operator, we had just also covered this slide. This slide has been also this emitter base junction. Yes, from this slide we are going to start base collector junction. Now we are going to study about the base collector junction. What is happen at the base collector junction while doing the biasing, or what the reaction of the electrons and holes takes place, and what about the depletion width at the junction. So due to the reverse biases, large number of free electrons in the right side N region collector, right side N region collector experience an attractive force from the positive terminal of the battery. Hence the free electrons move away from the junction and flow towards the positive terminal of the battery. As a result, a large number of neutral collector atom loses electrons and become positive ions. On other hand, holes in the P region base experience an attractive force from the negative terminal of the battery. Hence, holes move away from the junction and flow towards negative terminal of the battery. As a result, a large number of neutral base atoms gain electrons and become negative ions. Thus, the width of depletion region increases at base collector junction. In other words, the number of positive and negative ion increases at the base collector junction. Next, the free electrons that are flowing from the emitter to base due to forward bias will combine with the holes in the base. However, the base is very thin and lightly doped. So only a small percentage of emitter free electrons combines with the holes in the base region. The remaining large number of free electrons will cross the base region and reaches to the collector region. This is due to the positive supply voltage applied to the or applied at the collector. Both the emitter free electrons and collector free electrons produce current by flowing towards the positive terminal of the battery. Therefore, an amplified current is produced at the output. In NPN transistor, the electric current is majorly conducted by free electrons. PNP transistor, when a single N-type semiconductor layer is sandwiched between two P-type semiconductor layers, a PNP transistor is formed. The symbol of PNP transistor is shown in the given figures, the circuit symbol and diode analogy of PNP transistor. So the arrowhead from emitter to base is moving inside that differentiate the PNP from NPN. The transistor can be constructed by using one of the 5 basic techniques. Based on these techniques, they are classified as grown junction transistor, alloy junction transistor, diffusion junction transistor, epitaxial junction transistor, point contact junction transistor. Now, how the transistors are formed. The first is grown junction transistor. The grown junction transistor was developed on June 23, 1948 by William Shockley. It was developed 6 months after the first bipolar point contact transistor. The Czechoslovakian technique is used to form the 2p-n junction of a grown junction transistor. The NPN ground junction transistor is made up of a single crystal of semiconductor material, silicon or germanium. The impurity concentration of this semiconductor material is changed during the crystal drawing operation by adding N-type or P-type atoms as required. Alloy junction transistor. Alloy junction transistor. The alloy transistor or alloy junction transistor is a germanium BJT bipolar junction transistor developed at General Electric and RCA in 1951 as an improvement over the earlier ground junction transistor. The alloy junction technique is also called the fuse technique. The alloy junction transistor is made up of a thin wafer of N-type germanium material forming the base with 2 dots of indium acceptor atoms attached to opposite sides of the N-type material. The whole structure is raised to high temperature above the melting point of indium but below that of germanium. A tiny portion of indium dissolves and enters into the wafer of N-type material. Thus, the P-type material is created at 2 sides of N-type wafer. Diffusion junction transistor. The diffusion junction transistor was developed by Bell Laboratories in 1954. The diffusion junction transistor is a transistor which is formed when the N-type silicon wafer called substrate is exposed to P-type and N-type gaseous impurities. Diffusion is the process by which charged particle flows from the higher concentration region to a lower concentration region. The diffusion junction transistor use this diffusion technique to form the transistor. In this technique, an N-type substrate is placed in gaseous acceptor impurities and heated. The acceptor impurities diffuse into the N-type substrate collector to form a P-type layer based on it. Epitaxial junction transistor. The term epitaxy is Greek word composed of 2 parts, namely epi, which means on, and taxi, which means ordered arrangement. Thus, epitaxy refers to ordered arrangement on some materials. In this technique, a very thin layer of P-type semiconductor or N-type semiconductor is grown on a heavily doped substrate of the same material. If the substrate is N-type, a thin N-type semiconductor layer is grown on the substrate. In a similar way, if the substrate is P-type, a thin p-type semiconductor layer is grown on the substrate. Point contact junction transistor. The point contact junction transistor was the first type of transistor ever constructed. It was developed by Walter Brattain, John Bardeen, and William Shockley at Bell Laboratories in December 1947. The point contact transistor consists of a block of germanium semiconductor with two very closely spaced gold contacts held against it by a spring. A small strip of gold foil is attached over the point of plastic triangle. Next. Now, the topic transistor currents. We know that in transistors and diodes, electric current is carried by both free electrons and holes. Free electrons and holes travel in opposite direction. Free electrons and holes travel in opposite directions. For example, if the free electrons flows from left to right, then the holes will flow from right to left. However, the direction of holes is assumed as same as the direction of the current. When Benjamin Franklin started doing experiment on electricity, he believed that something is moving through the electrical wires. He named these moving thing as charge. At that time, people did not know about electrons and protons. Franklin assumed that there was only one type of charge, and this charge will always flow from higher concentration region, excess charge carriers, to the lower concentration region, fewer charge carriers. He called the higher concentration region as positive and the lower concentration region as negative. So according to Franklin, the charge always flows from positive to negative. We know that electric current means the flow of charge. So the electric current direction is from positive to negative. Transistor current components. The various current components in the Pnp transistor, which flows across the forward bias emitter junction and the reverse bias collector junctions, are shown in the below figure. The emitter current IE consists of hole current, IPE, majority carriers, holes crossing from emitter into base, and electron current, IME, majority carriers, electron crossing from base into emitter. Therefore, total emitter current, IE, is the sum of the hole and electron current. So IE is equals to IPE plus INE. The ratio of hole to electron current crossing the emitter junction is proportional to the ratio of the conductivity of the P material to that of the N material. We know that conductivity is directly proportional to the doping level. If doping level is more, conductivity is more. Similarly, if doping level is less, conductivity is less. In a commercial transistor, the doping of the emitter is made much larger than the doping of the base. Hence, in a PNP transistor, the emitter current consists almost entirely of holes. So this is the figure shown for the current components in the PNP type transistor. And the current components are based on the majority and minority charge carriers in holes by the means of holes or electrons at the different junctions and through the emitter, base, and collector. So in this way, if you are watching this, so this red line shows that because it is a p-type semiconductor, the holes are in the majority. So holes are moving in this direction because the positive terminal of the battery will repel the holes and they move in this direction, and the current and holes are in the same direction of the current. And as the electrons are attracting towards the positive terminal, so they are moving towards the positive terminal of the battery and result in the current which is in the direction of hole current. So it is mentioned as IPE and IEINE. So as when they cross through the junction JE, the IP is divided into two currents, and it result in one is IPC, that is hole current at the collector side, and the remaining IPE minus IPC just move through the base, and the reverse saturation current is just due to the minority in the p-type collector region. Okay, so these are the some current components. The basic component is shown as IE and the IB and the IC. So as we know that Kirchhoff current law, the incoming current is equals to the outgoing current, or all the current at the junction are algebraically added. So as we apply the Kirchhoff current law, then IE is equals to IB plus IC. Now the further current components are going to replace IB and IC. So this is the diagrammatic representation, and this is the nomenclature for the various current components. Now the holes crossing the emitter junction JE and reaching the collector junction JC constitutes hole current IPC in the collector. Note, not all the holes crossing the emitter junction. Not all the holes crossing the emitter junction JE reaches the collector junction. Not all the holes are crossing and reaches to the collector. Some of the are just diverted through the base, because some of them combine with the electrons in the n-type base. We know that base is very thin and lightly doped, so only a small number of holes combine with the electrons in the n-type base, constituting the base current IPE minus IPC. The remaining large number of holes cross the base region and enters into the collector region, constituting the hole current IPC in collector region. Consider for the moment an open circuited emitter while the collector junction remains reverse biased. When emitter is open circuited, the emitter current is 0, and therefore hole current collector is also 0. In such condition, the collector base junction act as reverse bias diode, and the collector current IC is equal to the reverse saturation current or reverse saturation collector current ICO. So I hope that the component of the currents through the bipolar junction transistors is almost very clear to all of you. Now let us return to the situation where the emitter is forward biased. When the emitter junction is forward biased and collector junction is reverse biased, the total collector current IC will be the sum of hole current IPC and reverse saturation collector current ICO. So again, we are going to use this equation in our calculations. Very important relationship. Transistor terminal voltages, the supply voltage polarities of NPN and PNP transistors are shown in the below figures. Supply voltage polarities of NPN transistor. The NPN transistor is formed by sandwiching the single p-type semiconductor layer between the two n-type semiconductor layers. The supply voltage polarities of NPN transistor is shown in the below figure. The supply voltage between the base and the emitter is denoted by VBE. The base is biased positive with respect to the emitter, and the arrowhead points from the positive base to the negative emitter. The arrowhead direction represents the direction of current flow. So, this is the symbolic representation which I had already told you, that arrowhead will differentiate whether it is NPN or PNP, and the arrowhead is representing the direction of current. Basically, the arrowhead is representing the direction of current depending upon the biasing in the forward bias and the reverse bias. Okay. The supply voltage between the collector and the base is denoted by VCB. The collector is biased to a higher positive level than the base to keep the collector base junction reverse biased. Supply voltage polarities for PNP transistor. The PNP transistor is formed by sandwiching the single n-type semiconductor layer between the two p-type semiconductor layers. The supply voltage polarities of P and P transistor is shown in the below figure. The supply voltage between the base and the emitter is denoted by VBE. The base is biased negative with respect to the emitter, and the arrowhead points from the positive emitter to the negative base. The arrowhead direction represents the direction of the current flow. This is for the PNP, which is almost similar to the NPN, but the biasing is almost in the opposite way, and due to that the current start flowing and the arrowhead representing the direction of flow of current. The supply voltage between the collector and the base is denoted by VCB. The collector is biased to a higher negative level than the base to keep the collector base junction reverse biased. Now, base emitter voltage VB for NPN and PNP transistor. The transistor is normally operated in the active region for amplifying the electric current. In active region, the emitter junction is forward bias and the collector junction is reverse bias. The typical base emitter voltage VBE for both NPN and PNP transistor are as follows. If the transistor is made up of silicon material, the base emitter voltage VBE will be 0.7 volt if it is silicon based. If the transistor is made up of germanium material, the base emitter voltage VBE will be 0.3 volt, or basically they are nothing, they are the junction voltage, or we can say that they are knee voltage or cut-in voltages. So these are the potential drops at the junctions. If it is silicon based, then it is near about 0.7 volt, and if it is germanium based, then it is near about 0.3 volt. Collector base voltages for PNP and NPN transistor. The typical collector base voltage for both NPN and PNP transistor will be anywhere between 3 volt to 20 volt, because it is almost in the reverse bias. So the range is very high, the voltage range or the voltage drop range is very high, that is 3 volt to almost in between from 3 volt to 20 volt. Types of transistor configuration. The transistor is an electronic device which is primarily used to amplify the electric current. We know that transistor has 3 terminals, namely emitter, base, and collector. But to connect a transistor in the circuit, we need 4 terminals, 2 terminals for input and other 2 terminals for output. But the transistor does not have 4 terminals. Then how do we connect transistor in a circuit? It is not as difficult as you think. One of the 3 terminal is used as common to both input and output when a transistor is to be connected in circuit. One terminal is used as the input terminal, the other terminal is used as the output terminal, and the third terminal is common to the input and output. So if you studied the 2-port network in the circuit analysis and synthesis, there we are finding Z parameter, Y parameter, H parameters and ABC parameters. So 2-port network, it is basically a 2-port network, or transistors behave like a 2-port network, and particularly H parameters in the network analysis and synthesis are bring out to study the relationship or analyze the relationship for transistor only. So 3-terminal device can be used for input and output by keeping 1 terminal common for input and output. In this way, the configuration or the connections are made. When transistor is to be connected in circuit, 1 terminal is used as the input terminal, the other terminal is used as the output terminal, and the third terminal is common to the input and output. That means here input is applied between the input terminal and common terminal, and the corresponding output is taken between the output and the common terminal. Depending upon the terminal which is used as common terminal to the input and output terminals, the transistor can be connected in the following 3 configurations. They are common base configuration, common emitter configuration, common collector configuration. So keeping base as common at a time, keeping emitter as common at a time, keeping collector as common at a time, we are using the BJT in 3 basic configurations, and after the analysis or connecting in these configuration, we come to know about some conclusion that a particular configuration is used for particular application, and it results something specific while keeping a particular configuration. So we can say that, for example, in a team of cricket, all the team members, there are 11 team members, and we can say that one is good in bowling, one is good in batting, one is good in fielding, one is good in wicket keeping, and every individual sportsman or every individual cricketer is specific or expertise to give his output in the field according to his uh, perfection. So similarly to that, the common base is in the analogy of cricket, we can say it is just behave like a good batsman. So if in the technical side, if we can say that it is used as a good amplification, similarly, common ammeter configuration results in something very somewhat like gain parameters, high gain, low gain, whatever it is. And there is some specific characteristic of the common collector. What will we get in the output after keeping the collector as a common and ammeter and base as the keeping collector to the common both the ports. So one by one, we are going to analyze these three types of configuration and learn what are the specific characteristics are to be obtained in the output after doing the such configuration of the BJT. In every configuration, the base emitter junction JE is always forward bias and the collector base junction is always reverse bias to operate the transistor's current amplifier. In common base configuration, the ammeter is the input terminal and collector is the output terminal and the base is the common terminal. The base terminal is grounded in the common base configuration. So the common base configuration is also known as the ground base configuration. Common ammeter configuration, in common ammeter configuration, base is the input terminal, collector is the output terminal and the ammeter is the common terminal. The ammeter terminal is grounded in the common ammeter configuration. So the common ammeter configuration is also known as grounded ammeter configuration. Common collector configuration. In common collector configuration, base is the input terminal, ammeter is the output terminal, and the collector is the common terminal. The collector terminal is grounded in the common collector configuration. So the common collector configuration is also known as the grounded collector configuration. Common base configuration. Now, in common base configuration, ammeter is the input terminal, collector is the output terminal, and base is the connected as common terminal for both input and output. That means the ammeter terminal and common base terminals are known as input terminals, whereas the collector terminal and common base terminal are known as output terminals. In common base configuration, the base terminal is grounded. So the common base configuration is also known as grounded base configuration. Sometimes common base configuration is referred to as common base amplifier or CB configuration. So this is the common base configuration for NPN type semiconductor or NPN type transistor. So the ammeter junction JE is forward bias and JC will be reverse bias. That means in the active mode, we need to keep the contacts or the connection of the applied voltage. The input signal is applied between the ammeter and base terminal, while the corresponding output signal is taken across the collector and the base terminal. Thus, the base terminal of the transistor is common for both input and output terminals, and hence it is named as common base configuration. The supply voltage between base and ammeter is denoted by VBE, while the supply voltage between collector and base is denoted by VCB. As mentioned earlier, in every configuration, the base ammeter junction JE is always forward biased and collector base junction JC is always reverse biased. Therefore, in common base configuration, the base emitter junction JE is forward biased and collector base junction JC is reverse biased. The common base configuration for both NPN and PNP transistors shown in the below figure. This is for the PNP type common base configuration. Now, as a result, free electron starts flowing from emitter to base. Similarly, holes start flowing from base to emitter. Thus, free electrons which are flowing from emitter to base and holes which are flowing from base to emitter conduct electric current. The actual current is carried by free electrons which are flowing from emitter to base. However, we follow the conventional current direction which is from base to emitter. Thus, electric current is produced at the base and the emitter region. The free electrons which are flowing from emitter to base will combine with the holes in the base region. Similarly, the holes which are flowing from base to emitter will combine with the electrons in the emitter region. From the above figure, it is seen that the width of the base region is very thin. Therefore, only a small percentage of free electrons from emitter region will combine with the holes in the base region, and the remaining large number of free electrons cross the base region and enters into the collector region. A large number of free electrons which entered into the collector region will experience an attractive force from the positive terminal of the battery. Therefore, the free electrons in the collector region will flow towards the positive terminal of the battery. Thus, electric current is produced in the collector region. Therefore, the common base amplifier provides a low input impedance and high output impedance. So, this is the characteristic for a common base amplifier or for common base configuration, that it provides low input impedance and high output impedance. So, transistor with low input impedance and high output impedance provide a high voltage gain. So, this will provide the high voltage gain. So, gain is just, we can say that efficiency of output upon input. So, high output impedance to the low output impedance will result in high voltage gain. So, the common base configuration results in high voltage gain. Even though the voltage gain is high, the current gain is very low, and overall power gain of the common base amplifier is low as compared to the other transistor amplifier configurations. The common base transistor amplifiers are primarily used in applications where low input impedance is required. Where low input impedance is required, the common base amplifier is mainly used as voltage amplifier or current buffer. This type of transistor arrangement is not very common and is not as widely used as the other transistor configuration. So the input characteristic describe the relationship between the input current and the input voltage. First, draw a vertical line and a horizontal line. The vertical line represents y-axis and the horizontal line represents the x-axis. The input current or ammeter current I is taken along the y-axis vertical line, and the input voltage VB is taken along the x-axis, that is the horizontal line. To determine the input characteristic, the output voltage VCB, collector base voltage, is kept constant at a 0 volts, and the input voltage VB is increased from 0 volt to different voltage levels. For each voltage level of the input voltage, the input current is recorded on a paper or in any other form, A curve is then drawn between input current and input voltage at constant output voltage. So this is called input characteristic. For common base configuration, this is the input characteristic for common base configuration. For common base configuration at 0 volt, 8 volt and 18 volt, collector base at collector base. Okay. So at 0 volt, that is collector base is at 0 volt. That means we just capped 0 volt and increasing base ammeter voltage. So we are getting the curve of IE, that is ammeter current, like this. And as we change the collector base voltage is equals to 8 volt and capped it constant, and we are just increasing the base ammeter voltage, then we are just getting the another curve of ammeter current, which is in the middle. And if we capped collector base voltage is constant at 18 volt and start increasing the base ammeter voltage, we are getting the ammeter current is the third curve. So while observing or while drawing the curve, we are observing that as we are doing the or increasing the reverse voltage or reverse biasing voltage, the ammeter current start flow earlier as compared to the unbiased, or we can say that collector base at equals to 0 volt. So this is the input characteristic of common base configuration. So in the next slide or in the next lecture, we are going to study about the output characteristic of the common base configuration. So for today's lecture, that is all for the today's lecture. Thank you all.